Taking a break from politics today, I want to address a scientific subject, cosmology. On a recent space show, Open Lines, I addressed some of the ideas that I've been thinking about the cosmological issue in the contemporary period. And basically, let's go back, many years ago when I was a lot younger, there was a lot of discussion about the basic geometry of the universe. And there was generally three categories that were in the Friedman, Robertson, Walker metric that's a solution of general relativity, which lead to three basic possibilities. One is the so-called positively curved or spherical universe, the flat universe, which is just think our traditional idea of space, and then the hyperbolic universe, which is the third possibilities. And there's a fundamental parameter in these solutions called k. Is k plus 1 is positive, 0 is flat, and minus 1 is hyperbolic or negative. Now, but this is very traditional stuff in cosmology, if any of you are familiar with that. However, two of these cases, the flat and the hyperbolic, are essentially topologically equivalent to each other. And the other one is topologically distinct. The positive or so-called spherical universe has a different topology, that of actually literally a hypersphere, that is a three-dimensional spherical surface in a four-dimensional embedding space. Okay, and that's just the standard stuff in cosmology. But what changed many years ago, roughly about the time I left school, was called the Inflationary Universe model. And this, Alan Guth of MIT was the primary advocate of this. There's many other people have joined. It's becoming pretty much the commonly accepted idea is that the very earliest instances of the universe, it went from a very small universe to a much larger universe in a very, very small amount of time. I think it's something like 10 to the minus 32 seconds or something like that. So it's shorter than short. By practical terms, you'd call it instantaneous. And although it literally isn't. And that process led to the idea that the universe was much bigger than we ever imagined. Add to it, the observational evidence over the decades have shown increasingly that the universe appears to be fundamentally flat. And so when we look at it from that perspective, however, the thing you have to bear in mind is it's so close to flat that, and with the idea of the greatly expanded universe due to inflation, it could be a positive curvature universe or a negative curvature universe, or literally a flat one, which would seem to be a little bit unlikely if it's a random process, only in that sort of like if you toss a coin and the flat universe would be the one where the universe lies on the side, on its edge, rather than either heads or tails. So, however, there's another theoretical idea that I would bring to it that I don't hear discussed a lot. Although I think Wolfgang Rindler mentioned it in his book, Essential Relativity. But essentially, think about this the following way. If you take the flat universe case as an example, it's filled with matter, and imagine that you could, like a movie, run the film backwards and see it going back in time, literally toward the beginning point at time equals 0. It would get denser and denser and denser, and so that essentially it always remains infinite. That's the key thing. The flat and hyperbolic universes are inherently infinite in extent at all times, whereas the spherical universe, is always finite, although large. Okay, so if we run it back in time all the way to the beginning, what we would end up is a universe of infinite density at time 0. Okay, every infinite in extent, infinite density at time 0. And that just seems to violate any kind of common sense, I think, particularly because immediately after that, the density becomes finite, of course, and it still expands everywhere, you see. And that seems to violate some really strange conceptual ideas. And the hyperbolic case has the same problem. So the logical solution theoretically still seems to be to go with Einstein and John Wheeler and those people to think that it is the K+1 hyperspherical case. All right. So if we accept that line of thinking, then, and remember that the universe is now greatly expanded due to the inflationary period, there is no real conflict with observational evidence within the error bars that we can observe. And so that gives us an interesting concept of the type of universe that we live in all probability. I still think that would be good. Now, that would give a universe. Now, let's discuss what hyperspherical really means. We can just think of a sphere like a globe or something, but in reality, it's a hypersphere. So what that really is take a sphere in a circle, and then at each point on the sphere, imagine that the point isn't a point, but it's also a circle. So you can move, and it's roughly equivalent in all directions, although probably not exactly, but it's close enough for discussion. Just like you can sort of think of the Earth as a sphere, even though it really isn't exactly spherical, right? So similarly speaking, you can imagine you can move in any direction in 3 dimensions and still be moving around, yet the actual volume, the 3-dimensional volume, think of that as analogous to the area of a surface of an ordinary sphere, is finite at any point in time and of course expanding. Now, another thing to throw into this is in the late 90s we discovered that the universe's expansion was accelerating. This is due to the process we normally now call dark energy, or it is just basically the old cosmological constant. It goes back to Einstein's first attempt to address these things. And if we recall historically, when we first got into this, we didn't even know about galaxies for sure. They were nebula, and we just thought there was a sea of stars out there. And so Einstein was trying to say, why doesn't the whole thing just collapse? And therefore, he created a cosmological constant in his general theory of relativity in order to counterbalance the attractive forces on a macroscopic scale to prevent it from all collapsing. Well, when Hubble discovered that the universe was actually expanding due to the red shift, that fell out of favor, and for a long time they took the cosmological constant out of the discussion. But it was always a theoretical possibility because the energy conservation is maintained by adding this constant into the theory. Essentially, now let's don't get into the math, but there's a mathematical reason for why that would be. Think of it as a constant of integration in a differential equation. It isn't exactly that way, but for practical purposes, you can think of it like that. And so you can set it to wherever it needs to be with initial conditions or whatever, as long as it's constant. And that seems to be the current standard model of cosmology on that. So we add that into it. What do we have? We have a spherical universe, hyperspherical universe that continues to expand essentially forever. It's essentially, think of it like it's escaped it moved past its own escape velocity, if you will. And essentially, you can almost look at the curve of the radius as being like a curve of something that comes back down to zero again, like a ballistic trajectory, except when it gets up to a certain level and before it hits the peak, it goes to an inflection point and then turns up and keeps on going in an upward pattern. So that would be the theoretical model that I'm proposing is the best one of the ones on the menu, if you will. And that allows us in the creation point to have a universe basically be very concentrated at the very instant. Not from an infinite spread of infinite density, but from a relatively, I guess you'd say, a highly dense or infinite dense point, sort of. And that will lead to a lot of other theoretical issues, of course, as to how that actually works. But we also know that will go to a point where current theories break down, and we'll need a quantum theory of gravity to address those issues at that beginning time. And so all we can do is to say that it originally was very dense and then it went through an inflation period. And beyond that, we're somewhat out of knowing what really could have happened. Anyway, that's just my view on the cosmological issue at the time. And you may have your own opinions on it. I'd be interested to see whatever comments you have, particularly anybody that actually has any actual formal expertise in the subject that could educate me some. I'm all about that. And as they say on these things, like and subscribe if you're interested. I'll try to add some scientific topics into this. these videos as time goes on. Thank you.